Let's now work on a frame with distributed loads applied to its elements. And we'll work on that through this example. We have a frame structure like this, made of two elements, element 1 here, and element 2, and 3 nodes again with these boundary conditions. Element 2 has a distributed load applied to it, and element 2 is at 45 degrees with respect to the global surface matrix, whereas element 2 is at 0 degrees with respect to the global coordinate system. And these are the values we're going to be using. Young's modulus of 210 gigapascals, should actually be capital P. L1 is at 30 degrees, so this is 30. So the length of element 1 would be 30 times square root of 2. And then L2, this portion is 40 meters. Cross-section area of each of the beams is 10 to the minus 2, and I is 10 to the minus 4. And this force, or this distributed load, is 10 kilonewtons per meter. So these are the steps that we need to do. First, for each element, we have to create the global surface matrix and local equivalent nodal forces due to the distributed load, and then using that form the local effective nodal forces. Convert the local effective nodal forces into global effective nodal forces so that we could use it together with the global surface matrix. For this one, we're going to need to use the transformation matrix, and then form the total surface matrix and the total effective nodal forces for the entire structure to relate the forces and displacements, and then write them in the matrix format, apply the boundary conditions, and solve for the problem. So this is the big form of the global surface matrix for a frame element. We could either use this equation or this matrix, or we could also use transpose of T, K, and then T to create the global surface matrix for a frame element. I personally prefer this method, but you could use any method that you prefer. So using that, I found the global surface matrix for element 1 to be here. Again, it's at 45 degrees with respect to the global coordinate system. And the corresponding degrees of freedom per column and per row are written next to them. So this is for d1x, d1y, phi1z for node 1, d2x, d2y, phi2z for node 2, and then the same for the rows. And I can actually divide this into 4 3x3s to study later. Similarly, for node element 2, I have a 6x6 stiffness matrix in the global coordinate system using the equations before, with the matrix before, and each column and row has its corresponding degree of freedom per node written to it. So node 2, node 3 columns, and these are node 2, and these are for node 3, the degrees of freedom per node. And again, I can convert or divide this into 4 segments. Writing the two 6x6 stiffness matrices next to each other, again, because node 2 is common between the two elements, I know that this portion of the first matrix has to be added to this portion of the second matrix, and the portion of the total surface matrix which relate the node 1 to node 3 degrees of freedom will have to be 0. So all the other elements of the total surface matrix will be filled with these values corresponding to their degrees of freedom, and only these portions will be added to each other. Moving forward, this will be the total surface matrix for my entire structure. It's a 9 by 9 matrix, and that's because we have 3 nodes and 3 degrees of freedom per node, which means we're going to need a 9 by 9 total surface matrix. Again, these zeros here and here are because node 1 and node 3 are not attached to each other, and this portion shown by this rectangle area, is for node 2 because it's attached to both elements 1 and element 2. As a result, the values of the global stiffness matrices will be added there. So for the first element, I don't have any distributed forces. As a result, the equivalent nodal forces would be equal to a vector of 6 zeros. And I only have the local nodal forces, which would be the reactions at each node. I have F1x, F1y, M1z, F2x, F2y, and M2z, which, depending on the nature of the problem and the boundary conditions, some may be known and some may be unknown. So the effective nodal forces for the first element, which is equal to the equivalent nodal forces for the element, which is again all zeros, plus the nodal forces that I'm looking for, is going to be that. However, for the second element, I have distributed loads applied to it. And we know from the beam lecture that this would be the equivalent nodal forces. Now I have a 0 here and a 0 here, and that's corresponding to the x direction of the equivalent nodal forces, which would be 0 because when we studied beams, we didn't consider the longitudinal forces. But in frames, we have to use them, and as a result, we'll have a 0 here and a 0 here, and the rest are going to be exactly the same as the beam. So minus QL2 over 2, because the length of this beam is called L2, and then minus QL2 squared over 12, and then minus QL2 over 2, and then QL2 squared over 12. And the forces, or the nodal forces that we're looking for, depending on the boundary conditions, they could be either reaction forces or external forces, are written like this in the x, y, z direction for each node. Now here, effective nodal force is equal to equivalent nodal force plus the nodal forces we're looking for. And this time this is not 0, so we're going to have to add these two 6x1 vectors to create the total effective nodal forces for element 2. And then going from there, we can solve for the problem.